we are going to talk about some DFX fundamentals that reduce costs and decrease turn time. This is actually a really long presentation. It's about 90 minutes, and we're not going to do it all in one day. That would be ridiculous and probably boring. So we're going to split this up into two parts. The first part is going to focus on design for manufacturability, and the second part is going to focus on design for assembly. That'll be next week. Your presenters today are the wonderful Elijah Gracia from Royal Circuit Solutions in Hollister, California. And me, I'm Mark Hughes, also Royal Circuits, except in Santa Fe Springs. So Elijah, introduce yourself. Tell us a little bit about you.
Hey everybody, can you hear me?
Yeah.
Awesome. I'm going to try not to move this cable. So my name is Elijah Gracia, and I've been working here at Royal Circuits in Hollister for the last 6 years as a CAM engineer. I also am in charge of a lot of the special projects we do here. So if you guys ever have special projects, I'm sure you will hear from me.
What's an example of a special project?
A special project would be something like trying out new material or a new process that maybe you got done at another shop other than Royal and something new to us. Or something like these small projects like these ornaments. That's also me behind the wheel there.
Nice. So if it doesn't work out, we know who to email then, right?
Yep, that's going to be shipping at royalcircuits.com. No, I'm just kidding.
Just give them somebody else's email. That's what I would do. So, so I'm excited about that. This is our first time doing this, right?
Yeah.
Cool. And it's free. So if you're interested at all, just go visit the blog site, royalcircuits.com, and we'll get going. All right. Again, my name's Mark, and I'm in charge of, I really don't know what they pay me for, Elijah. Do you? Just as long as the checks keep coming, I am other duties as described, would I guess be the best description of what I do for us. So with that, let's go and get going. So we're going to just talk about design for manufacturability today, process overview, design choices, talk a little bit about things that will hopefully make you, let's just call it, more educated about the process so you make better design decisions. And the next time we'll do the design for assembly. All right. So Elijah,
yes,
DFX,
sir.
right? The X can stand for anything. In this case, we're doing DFM. Do you want to cover that and then I'll do assembly?
Definitely sounds good. So let's jump into it. Design for manufacture. Basically, this is asking the question, can the board be built? Just because you punched in your data into some fancy software doesn't mean that we're going to actually be able to build your board. There's a lot of things that come into play. Each shop has their own specs and capabilities. Royal Circuits has, I'd say, some of the most advanced from what I'm seeing out here, but there's still some things that we can't do. 1 mil traces is still not a thing. So yeah, basically this is just what we do at the very beginning. Once we get your board, we punch your design into our software and we kind of guide it and check and see if we can actually build your board.
Yeah. One thing I'll add there too, we offer free DFM. Even if you don't use our services, we've got software and we're hopefully, we keep hearing it's going to be on our website where you can just plug your data in and go. But if not, shoot it over to sales. We can run a DFM check and have it back to you, within minutes if somebody's watching that email account, right? So the next thing
definitely.
is DFA, design for assembly. Can we actually put your board together? Can sometimes people will put the parts too close together or they'll have the wrong land pad patterns and we just can't do it. But it's actually a little bit more complicated than just, can we do it, right? Because we can do a lot of things. You can also drive with your feet. It doesn't make it a good idea. See, the next thing you need to worry about is yield. And what's yield, Elijah?
Yield is going to be basically how many boards we're going to get, good boards we're going to get, because there is that factor of, some of those boards aren't going to be good when we make them. Some of them are going to be etched off a little bit on one hole. And again, one wrong hole or one bad trace and the board's no good. So it's something you have to take into consideration.
So what would a good yield be?
For us, we try to stick to 90 to 95% yield. We can usually do that. Basic designs, they're at 100 right now. We're doing really good Haven't seen a simple mess up. We keep track of all that stuff. So basically, when you're ordering 100 boards, you're going to want to make 110, maybe 120 boards based on the design. And something you have to keep into consideration.
Wow, very cool. So Greg Zeraldo was over at Advanced Assembly. He's the process manager there. And he says this, right? Design for acceptable yield is really what DFM and DFA means. Acceptable yield without requiring expert machine operators to walk your board through every stage of the process, right? We've got people who have been building boards. I mean, how long have John and Matt been around? 15, 20 years?
Yes.
Right? They can make things happen that I can't, right? And some new guy working the line can't. But you're going to have to pay them to do that.
Right.
So it's not just about, can we build your board? Can we build it economically? Can we build it easily? Can we do it and still get a high yield? Because fabricators don't accept risk. If we're a little worried about a panel coming out and we think that we might have to make this panel 2 or 3 times, we're billing you for 2 or 3 panels.
Exactly.
And that's every fabrication shop. So the idea is to reduce risk as much as possible. And part of that, is reducing the number of steps it takes to build your board. So Elijah, I was blown away when the first time I ever came to the shop and I saw a traveler that, this thing was like an inch thick for some project. What are travelers and what are some of the steps that a board goes through before we jump into them?
Yeah, so a traveler is basically going to be a custom blueprint for each board that we build in the house. Once you send us your design, we run through it DFM. We see what you're going to need, what you won't need, and we're going to put this little traveler together based on your specific job. No two are the same. We're going to have the stack up, the way we're going to build your board exactly, kind of how they're going to stack up the sandwich. And then we have a step-by-step process of every single procedure that they're going to follow in order to build your board. Because the production team on the floor, they have no clue what's going on with this board until they're halfway into it, So we have to give them exact designs because we are seeing the inner layers. We're seeing the different drill cycles and stuff like that. So this is basically the blueprint that we're going to have. And like Mark said, some of these are 2 pages long. Some of these are an inch thick. All depends on what your design's got.
And you'll hear some shops, they'll talk about moving to, electronic travelers. How can anything ever be done in paper in this day and age? It doesn't matter. It's an accountability and traceability requirement, whether it's, paper or electronic. It simply moving to an electronic medium doesn't mean you're going to get a better board out of the other end. What you want to do when you're creating your board is figure out how to have as few steps as possible and still get this board made. Fewer steps, it's going to happen faster and there's going to be less risk. And we'll talk about some of these different steps as we go through. But another thing too is it's not all about putting your board together. You've got to be able to get your board apart at the other end after assembly. So when you design your panel, it's got to be strong enough that it stays together during shipping and doesn't spontaneously depanelize. And then it's easy enough to come apart at the other side. And the 2 ways that you can do that are with V-score and routing. V-score, we take a precision drill and we cut about 1/3 of the way through the board on either side. And routing, we have this blown up in a second. I see that image is kind of hard to see, but the other common way of doing it is with these things called mouse bites. So when you're designing your project, one of the things to keep in mind is, how is this thing going to be taken apart at the end? How are we going to individualize it? So I assume that running a drill straight down the center of it, that probably makes sense to you, but it gets a little more technical when we get over to the mouse bites. You want to tell us a little bit about that, Elijah?
Yeah, so mouse bites are one way to separate your board. Usually you're trying to keep rails on the outside of your board to help you through assembly if your assembly shop requires that. And so what it is we're leaving these little tabs of material right in that center, that 150 mil in our case. And then what we're going to do with that little tab of material that's holding onto the outside rail is we're going to punch 5 holes right in the middle of that. And so if you apply enough pressure, it's going to crack right off and snap right there without affecting your board. And this is usually used when you have an odd shaped board. Something like V-score can only be used
There's
on a
like
square
little
board.
passives, O201s, whatever. They'll snap right off, won't they?
Exactly.
So when you're creating your board, you need to make sure that you're not putting very sensitive components in those stress areas. And another thing to keep in mind too is when we route, we route out your panels. To get a good clean edge, we've got to make two passes, one up one side and one down the other. Otherwise, I forget the names. Is it cutting edge, the trailing edge?
Yes, cutting edge.
So the cutting edge will give you a clean cut, but on the other side, I think is that the climb?
Yeah, you have the blade basically facing the opposite direction, so it's going to look pretty ugly.
Yeah, it just drags across the surface and just makes a big furry mess. You don't want that in your final design. So when you talk to your fab house about what size router cutters they use, if it's a 70.9 as we tip, that's our favorite one. We don't make a 70.9 mil hole. We make a 100 mil hole or a route path, just so it goes up one side and down the other. And Elijah was talking about rails a second ago, and those are the parts of the panel that we can put test coupons on, that we can use to put tooling holes to align everything. You've got to figure out how those things are going to come apart too. And you need to make sure that when it gets over to assembly and these things start getting broken apart, we're only breaking along straight line paths that cut clear through the board. So for this example, if we were going to depanel this one, individualize these boards, you'd break the top rail and the bottom rail off, and then you would break the two side rails off, and the rest of these would just fall apart. You never want to be in the situation like you see over on this right-hand side, where you've got a 90-degree turn. You're going to end up putting a ton of stress on the board when you start trying to take this part apart. So give multiple break paths so that whatever you do, it's always going to be a straight line. Elijah, do you have anything to add to that?
Yeah, if you can in the design phase, just say that you want breakaway patterns and let us do our standards. We'll add them. We'll make sure it's in the right space, make sure there's enough space between, give you the best option so that your board doesn't have to go through that extra stress.
Yeah, it's just a computer program for us, right? It's easy.
Exactly. Very
easy
easy.
peasy. All right. Earlier you said, with us, the type of manufacturing that we do, the subtractive, it's very difficult to get like 1 mil copper trace width. Can you tell us a little bit about our current manufacturing minimums, our process minimums?
Yeah. So the easiest way to say it is the thinner your copper weight is, the thinner trace we can do. The description we kind of use for that is if you got something as thick as like 6-ounce copper, basically my fingers will be able to pinch that trace and rip it right off the board. If I'm rubbing it with my finger, it's going to rip off. It's going to want to rip off the board unless it's a really thick trace that has a lot of surface to be able to connect and I guess adhere to the surface, right? So the thinner copper weight, the thinner the trace. Thicker the copper weight, those traces get bigger. If you look on the chart on the left, if I'm using 1/4 ounce, which is the smallest copper weight that we use, we can go all the way down to a 2.5 mil trace, which is pretty darn thin. We consider a hair on your head to be 3 mils. So I'd say that's pretty darn good. And then if you go up to like a 6 mil copper weight, we do go heavier, but for this chart's sake, 6 mil copper weight, it's going to have a minimum of 15 mil trace size. Oh, I'm sorry, 9 mil trace size. And you have to have those at least 15 mils apart because we're going to have to increase that trace size with edge comp.
And the last time I made this chart, last year, we actually had different numbers for internal and external copper layers, but we've eliminated those, right?
Correct. With the help of some new machines, we're actually able to get the exact same 2.5 mil trace on an inner layer now that we weren't before. Before it was 3.5, which is a whole mil.
Yeah, that's pretty cool. One of the other reasons too is that copper doesn't etch straight down, right? When it starts etching, it starts kind of curving a little, and if you keep going down further and further, you get to almost a trapezoid shape. You don't get straight vertical walls unless you over etch your your project. So you've got to make sure that there's enough room for that etching to take place. So one of the reasons with the thicker copper that we need the wider traces in space, it's not just the adherence and the or the adhesion of the copper to the board, which is really low, by the way. I mean, copper adhesion is measured in this unit called a ply, and it's roughly on par with, blue masking tape. It's not really all that strong. So more surface area, more strength, and it's also more room for etching.
Correct.
So, interesting stuff. It's a weird unit, I'm telling you. What about board thicknesses, Elijah? Like I just ordered some little LEDs, these RGBW ones, and I mean, I can bend this stuff like it's paper.
Right.
Versus we've got one of our clients who's making things and he wants his board rigid as possible, so he's got this thing up to like 3.2 millimeters. It's ridiculous. What's some advice you have there on designing around copper thickness, or I'm sorry, about board thickness?
Yeah, if you can stick to our tolerances, or I guess our standards, which is going to be 31 mils, 62 mils, 93 mils. We've tried finding out where these numbers come from. It's just been the industry standards since the beginning of circuit boards, as far as we can tell. So these type of materials actually can help these thicknesses can help your cost as well, because we already have material that's made to meet these thicknesses all day, every day. A majority of our boards are coming in at 31, 62, or 93. So we have plenty of material to do these all day long without you having to order special material or have something be not in stock,
Very true. Now we can do off sizes if you need to. It's just faster, cheaper, easier if you stick to the standards, right?
Exactly, yeah. I think thickest board we made was about 1 inch. It was a pretty pricey board, but extremely thick.
1 inch thick board. Man, I would have loved to see that.
Yeah, I have a coupon somewhere. It was huge.
Wow. All right. What about other process minimums, like our minimum mechanical drill?
Yeah, so our minimum drill size for the smallest drill that we use is a 5.9 diameter. And the reason for that is anything thinner than that, and you're going to be trying to push a noodle through a piece of wood. It's just not going to want to do it. The drill bit's going to bend and break over and over again before we ever get through that board. So keep that in mind, 5.9. And we also require a 10:1 aspect ratio, which means a 5.9 drill can only go as thick as 59 mil board thickness. If you try to punch that through 1 inch, it's just not going to happen. So keep that in mind. The other thing would be our laser drills, which we can go as small as 1 mil diameter, very small. And that's a 1:1 aspect ratio. So if you've got a 5 mil board, the smallest drill we're going to be able to do is a 5 mil drill. And usually those are done between processes, not usually through an entire board.
Do you happen to know the annular rings off the top of your head while we're here?
Yeah, so copper annular ring, we're going to want 5 mils for a standard drill. We can go a little bit smaller, but we really like to see 5 mils. And then laser drills is actually going to be as small as 2. Those laser drills are extremely accurate.
And are our mechanical numbers going to go down with the installation of these new machines that we just got?
Yes, we are currently testing our new tolerances. We just got quite a bit of new drill machines, and they're amazing with speed and accuracy. Yeah, it's a joke right now that we're gonna have to let some people go because they've got nothing to do back there.
Hey, I'll put on a nice suit and come up there and fire people.
Please do.
It could be fun. By the way, as we're going through this, if any of the listeners have questions, feel free to ask us in the question and answer box. We're not monitoring chat, but we are monitoring the Q&A. All right. When I submit my artwork, right, as a designer, I send my artwork to you. What happens to it? Do you guys just put it in the machine and hit print, or I mean, what do you do?
Yeah, F5 does some amazing things these days. But no, what we do with your board is we take your design, we usually plug it into the DFM check before we quote your board, just to make sure we're not missing anything, you're not missing anything. We understand some customers have multiple designs they're working on at the same time. So they might forget to mention that this job has laser vias, micro vias, whatever it is. So we checked through all that. Once I get your board in engineering, after it's been confirmed, the PO has been sent, what we do is run it through our DFM and DRC checks, which is kind of just redoing it again, a little more fine tooth comb. And I'm just making sure that you're meeting all of our minimum requirements, making sure that we can actually manufacture your board. I'm the one doing the etch comp for your board. Like if you want a 5 mil trace, I got to make sure we got room to bump it up a bit so that we can actually finish at your 5 mil trace. All the rules that we've talked about so far, we're just verifying those and making sure it's going to work out. So if you look at the submitted artwork, you've got one size pad or one size trace, and you go to the modifications, it's just slightly thicker. I'm just increasing everything a bit because when we put your board in the tank and it starts etching off copper, it's going to etch off more than what we designed. Like Mark was showing in the photos, it's kind of etching in that weird U-shaped pattern, and it's eating up a little bit more on the top than it is the bottom. So you're going to kind of get, it's not quite pyramid shape. I don't even, I guess what shape would you call that?
Trapezoid is usually what we describe.
Trapezoid, there you go. So it's a little thinner on top than it is on bottom, but at the bottom base, you are getting your required thickness. So we just got to keep a watch for all those things and design the board accordingly.
Very cool. I mean, the things you learn that happen to your board after you submit your artwork, right? I had no idea any of this existed before I came to Royal. It's
right.
mind-blowing.
You place the order and just wait for the boards to get there.
Pretty much. I mean, I'm much happier that way until things don't work, and then I'm sad.
Exactly.
So,
that's why it is good to know the process of things.
Yeah. All right. So let's keep talking about processes. We've got plenty of time here. Lamination, right? Tell me about what this does.
Lamination, that's basically we are building your sandwich, right? We've already made your inner layers, and what we're going to do is create the sandwich kind of like we explained on that Traveler. Each job gets their very specific order of the sandwich needs to be made. We have our rules with that too. I won't go too far into that, but so now we're laminating your board. We're using heat and pressure applied by this machine right here. And what it's doing is based on whatever material you're using, we have recipes on how much pressure should be applied, how much heat should be applied, how fast or slow it should cool down before we pull it out, so that we can get the best adhesion so that you don't have to worry about any delamination happening once the board gets to you.
So what kind of pressures and heat and times are we looking at to cure the epoxies in this?
That would be a little bit more of a Matt question than it would be me.
Okay, that's cool.
Yeah.
Can you tell us anything about the lamination machine that we're seeing there in the photo on the left?
Yeah, so on that right side is where you're able to put multiple, we call them books, which is basically one panel or one stack up, one sandwich. And we just put a pretty thick sheet of metal in between each book, and we're able to do multiple jobs, multiple panels at the same time. We do have a lot of standard materials, like we're saying. So as long as a few jobs are using the same standard materials, we can throw them all in at the same time, and they're going to cure at the same time.
Very cool.
Yeah.
All right. So after it goes through there, we flash route. Yeah.
Yeah. So all that is once we laminate your board, you've kind of got all this pre-preg that's been melted, this copper, and it's kind of oozing out of the sides, very ugly like. It doesn't look pretty, and it can cut your hands up pretty bad. And this board has to go through the rest of the shop. So what we do really quick is just take a router and give you a nice smooth edge all the way around. It also tells us that this board, we put a cut in one corner. And what that does is tells us this board has been made. There's inner layers, because again, we can't see the inside once it's been laminated. Whatever's inside is stuck inside, and we won't be able to see it. So we give it a cut in the corner, and that tells us this is an actual customer's board that has inner layers, because if you look at it, technically it could look exactly the same as a blank, thicker core, and we wouldn't be able to tell the difference.
Very cool.
Yeah.
Okay. Then, I mean, we can drill or we can laser drill, right?
Correct.
What does that process look like?
So laser drill, this one was pretty fun for me to start to learn. I work closely with the guy who does all the laser drill here. And what it actually does is it's not a laser hitting your board. It's a laser bouncing off a mirror, bouncing off of another mirror, and eventually hitting your board. And it's not actually just focusing down and burning into the material. It's actually going in a very tight circle pattern until it gets deeper and deeper and deeper. And basically it just keeps going until it hits copper. Once it starts reflecting back to itself, it knows to stop. It knows it's hit copper and it's done its job.
I didn't know it detected. I assumed it was all just calculated very carefully.
A little bit of both.
Very cool. All right. What about the mechanical drilling machines?
Yeah, so our mechanical drilling machines, these are actually the old ones. We'll have to get you some pictures of the new ones we just got in.
Yeah.
But they'll have about between 4 and 6 panels wide. We can do them all at the same time as long as it's the same job. And what they do is they just load the little drill bits into a little cartridge. There's a pretty big box of standard tools. Once I've created the program, I send it to that department. They pull in the program, load the panel on, and all they do is hit the go button. And it's going to grab each drill bit, drill every hole that needs to be in there at whatever size it needs to be, and wait for it to finish.
Very cool. And then I know that, you either use the laser drill and it's going to leave some debris, some charred remains in there, or use the mechanical drill and it's going to smear some epoxy. So next up, you've got to clean out those holes, right?
Yeah, so that's what we use at deburr, desmear. We have these special tanks that kind of just burn through it ever so lightly, just enough to get a smooth edge, because like anything, if you drill through wood, you're going to have that pattern still in there, all the wood chips still sticking out, right? It gets the same thing with copper and that fiberglass prepreg we get.
Very cool. And that's important, right? For if we're going to do any plating, we need exposed clean copper if we want to get a good via.
Exactly. The whole point of that hole is to get some copper in it, right? So let's start with a clean barrel.
All right. So then next, we've got these lamination machines, yeah?
Yeah. So a dry film mask, what that's going to do is we're going to take your panel now that the holes have been in it. And we're going to put this film and cover the entire panel. After that, it's going to go in a special laser machine. And what it's going to do is burn the image into that film that we just etched into it. So what it's doing is kind of just burning that film off, exposing certain areas. This is how we're going to get your exact design that you designed. So we wash it. Whatever was burnt is going to wash off and it's going to be cleared. And so what it's doing is that yellow film, if you look on your right side, that's covering everything we don't want to etch off. And
all right.
So, yeah. And so that's what we're doing when we're washing it off.
And then,
now,
go ahead.
Go ahead.
I was just going to say, don't we use some form of a electrolysis catalyst, something to put in there so that when we start doing the electroplating, it's got something to start conducting upon?
Yeah, that's one of the tanks right before we actually plate it. So now that we've exposed everything you need to see, what we're doing is we're dipping in the tanks and we're going to start. If you look on the left side, you still have your copper on certain layers, prepreg, separating it. Now we got to get that barrel all the way through, right? So the right side, once we put it in the tanks, we start plating all the way through. And like we said, different sizes, different thicknesses. We have different recipes for how long they need to be in there and at what voltage.
All right. So it gets electroplated, and then we've got our traces and all our pads and everything built up. The barrels exist now. And what do we do next?
Yeah, so now we are ready to get rid of everything else so we can wash off that film that's still on there. It's called resist strip. And all that's doing is whatever was meant to resist will now be stripped off. And you look on the right side now, boom, we have exactly the opposite of what you first required.
Interesting. And then
we go to the etching. What this is doing is eating off copper off of the entire surface. And we plate up extra on that last step so that once all the copper, everything else that's not raised, that's all going to get eaten off. That's the easiest way to say it. And what you're left with is your actual design, copper that's separated from pad to pad, no shorts, no opens. Everything's looking really clean, exactly like you designed it.
Interesting. And then at that point, we can either put it back in and, laminate some more, so those become internal layers, or we can move on to solder mask. And since we've already seen the other layers, let's move on to solder mask application.
Yeah, can we go back to the last slide really quick?
Sure.
This is one of the cool things that I really like about our shop is the AOI machines. And what we're doing is we have your design, right? We have it etched off onto a panel. But at this point, the person who's looking at your panel has no clue what it's supposed to look like. It could be missing something completely and they wouldn't know it. So we send a file to this AOI machine, which is automatic optical inspection. And it basically takes a image of what your design should be. And then this machine has a camera that takes a picture of the entire panel bit by bit. And what it does is it lays them on top of each other and compares it. And it's going to tell the operator every single place where there's an error, every place where maybe something's missing, maybe where there's too much copper. Most things can be fixed right away with a little razor blade and just chop off some copper. Or it'll tell you that the panel's no good if that's the case. Really cool machine. I like watching them do their job on this one.
That is cool. By the way, I picked up some lenses for these things at auction back when we got that new X-ray machine.
Oh, nice.
So yeah, I've got a bunch of telecentric lenses. I got to show them to you sometime. They are the coolest thing ever. So, all right. So, so after we pass AOI, hopefully, right, then we move on and we now need to start putting on some liquid photo imageable solder mask. What's this process look like?
Yeah, so if you've ever seen like screen printed t-shirts, it's basically the exact same thing. What we're going to do is create a screen for your job and then place it on top. It's a little more technical than that. You have to burn the image onto some film to create the screen. But once it's ready, it's exactly the same with a handheld squeegee and some paint that covers your board into the design you need to. We do have an automated machine now, which does do most of our work, but we still also do some handheld work as well.
Very cool. And then after we cure that in the micro steam ovens, and I could probably expand that section at some point, then we move on to putting your legend on, yeah?
Yeah, like you said, those micro steam ovens, the old way, probably about 2 years ago, was putting it in an oven for a couple hours. Now those micro steam ovens can cure your LPI in about 15 minutes.
That's crazy.
Yeah.
All right. So we've got two different screening processes, right?
Yes. So now your board's been painted. Basically, it's that green, right? Depending on what color you chose, but standard industry is green. Now we got to put the legend on, the silk screen, all the legend that's telling you where to put what parts. Maybe it's got your logo or our logo and the date code. Two ways of doing that. The first one is basically the exact same as that hand printed screen. We make a screen, we squeegee some paint over it, and bam, you got your LPI. One of the new things that we recently acquired was our direct legend printing. And it's basically a big jumbo printer that actually prints the text onto your board. It's pretty cool. The old handheld method takes a few hours into the process, whereas even the most complicated panel on a legend printer maybe takes about 5 minutes.
That's crazy. What about the quality difference?
So the direct legend printer does lose a little bit of quality and clarity. It's basically printing in tiny little dot patterns. For most jobs, it's not a problem at all. There are some that require very fine lines that it's not capable of, which we'd go to the old school method. But I believe we're actually getting a new printer soon that's going to be able to compete with those old silkscreen methods.
Really? That'll be cool.
Yeah, it's going to be fun.
And a question I sometimes get at trade shows, when we're working the booth is, can we do more than one color of silkscreen?
Yes, absolutely. LPI or silkscreen. I've seen boards that have multiple colors of the LPI and the silkscreen. It's really cool. Tells them which different parts to put on, or there's a company, I forget what their name was, but they were making kind of like a do-it-yourself PCB kit, something for starters, and it was all color-coded, told you which components to put where based on colors, and really cool.
Oh, very, very smart idea.
Yeah.
So, all right. What about other testing? What else do we have?
Yeah, so we have the main testing we use here is flying probe, and what that's doing is again, when we ran your board through DFM, we created a test program, basically a map of every possible connection that should or shouldn't be happening on your board. And so we send that to the test machine. The test machine loads the panel, and it's got these tiny little 2 probes in the front, 2 probes in the back, and oh man, the speed on these things are amazing. You can't even really see them testing as fast as they go. And it's testing every single point that needs to be tested on your board. Pretty cool machine.
Yeah, it's checking every net for connectivity wherever it can, actually get to a spot. And it's also looking for short circuits between nets, which is just insane. It'd be impossible to do this by hand.
Oh yeah, absolutely.
It'd take, weeks to do what this machine can do in minutes. It really is fast. All right. So with that, let's drill down into a couple subtopics. And again, guys, we're still happy to take any questions that you have, but that's kind of the overview of the fabrication process. Now we're going to get into a couple specific topics, and then we're still on time to get you out of here at 11:45. So we're still doing great. We've got time for questions if you guys want. With PCB construction, what's the difference between cap and foil that I hear about so much?
Yeah, so basically there's 2 types of foil in the circuit board industry. The first one would be just foil construction. That's a solid piece of copper on your right side, on the top and bottom. Yep, just a sheet of copper, and that's going to be your outer layers usually.
Whoops, sorry.
The other type would be a core, which is a top and a bottom piece of copper that's already been laminated with prepreg in the middle. And that's basically already cured. That's how we do our inner layers most commonly, like you see on the right side. But some customers do require cap construction, and some common reasons for that would, I guess the most common would be a hybrid construction, meaning they're using something like a Rogers material on the top, and the rest of the board would be an FR4 370HR material. 2 different materials, but they can actually be laminated together. The only rule that we have is if you use 2 different types, they must be cores. You can't use 2 different types of prepregs on the same stack up.
Interesting.
Yeah, and like we spoke about before, the reason for that is they have 2 different recipes. One of them will melt and completely disappear, while the other one still hasn't even heated up yet.
Interesting. Something I hadn't considered. Thanks, man.
Yeah.
So that's cap versus foil. And you guys prefer foil, sequential stack-ups whenever you can, right?
All day long. It helps us out with registration and just makes the board so much faster through the shop.
Okay. So one of the differences between the core prepreg and STACKUPS is the fiber to resin ratio, right? With core material, this stuff is made in a factory somewhere. Everything is very well known. You've got solid copper on top and on bottom. You can use a lot more fiberglass and a lot less epoxy. But when we've got prepreg, right, this is going to go on copper where there might be traces already cut into it. We need epoxy to squeeze out and fill in those gaps. So prepreg, as a rule, tends to have more epoxy than core material. That can be a problem from a signal integrity standpoint. If you guys are creating your design and you've got traces running over this stuff, if you're not careful and you've got something going over 106, which is a pretty common prepreg 1080 too, right? If you have the copper traces running over this, it's seeing huge impedance discontinuities as it transitions from glass to epoxy, from glass to epoxy, from glass to epoxy. So just something to keep in mind, and it's something we can talk about in greater detail. We have a whole separate presentation just on it. But if you look at this image on the left, you can see some of the different fiberglass types that are used in this particular cross section, right? You can see the STACKUPS. And some of them, you're looking at a ton of epoxy. Some of them, you're looking at a ton of fiberglass. So just something else to keep in mind too. If you do have signal integrity issues, the core might be the way to go, or routing on the layers that are surrounding the central core might be better for you. But if you want a whole separate presentation on that, let me know. One other thing I will mention though, is when you're designing your board stack, somewhere along the way, electrical engineers got the idea that they need to have outer layers as their signal layers. And, maybe this layer 2's VCC and layer 3's ground. And that is a horrible stack up because you cannot couple return paths through copper planes. It just simply doesn't work, right? Going from layer 1 to layer 2, in this particular stack up, we've got 8 mils of distance. And layer 1 to layer 3, right, if you're trying to couple back to your ground layer, 48 mils. Your signal's not going to couple back through there. It's going to go back through layer 2 more than likely, depending, all things considered.
Exactly.
So it's usually better to use a mixed stack up where you've got a mixture of power, ground, and signal, so you can keep these things, the return paths, as close as possible in your design. But again, that can be a whole other webinar if you guys are ever interested in hearing it.
Yeah, that's a great point.
Hey, buddy, tell me about vias. How are vias made?
Yeah, so this is really cool. I love this illustration that Mark put together. Basically, what we're doing is creating a hole and plating it, right? So we're starting with a solid sheet of copper, which is that nice little Royal Circuits logo. It's a solid sheet of copper. First step we're going to do is drill that hole. After we've drilled the hole, what we're going to do is cover it with a dry mask. That dry film is going to, expose the shape of whatever your design is. After that, it's electroplated. That barrel is filled with copper, as well as the exposed copper trace and pad that we have right there is also plated up. After that, we're going to strip off that film that we put on previously. And the last step is to etch. And etching is going to eat off all the copper now that was left covered from the beginning. And that's how you are left with your actual design, that nice little trace and pad that you designed or whatever it is. Perfect. That's the simplest way to explain a via.
And the only reason that I did that is so that we could talk very briefly, and this will be our last slide, about the different types of vias. So what can you tell me about them?
Yeah, so what we just looked at was the most simplest through hole, nothing special, top to bottom connection, right? So now we start getting into the more complicated things. A buried via, which is a via that doesn't reach the top or the bottom, it's buried inside of the board. And that's usually done through a small step in the middle when we're making the inner layers. We just drill a hole, plate it, and either copper fill it or epoxy fill it. We don't want to air bubble there. Once we get to lamination, that'll pop and blow your board up. Then we have a blind. A blind is basically hitting one side, not the other. It doesn't go all the way through the board. And that's similar. We create that inner layer buried via. And then once we add on the other layers, we're going to laser through the top section all the way down to that next via. Then we have through holes. That's what we have already explained in the previous slide. And then we get on to these other two, which are stacked. Stacked is when we make a hole in the very center of your board. And we just, every time we keep adding layers on the outside, we laser drill through that again and plate them shut. And what that's doing is creating a solid hole all the way through for something that's very tight, or when you need something like a blind drill that's going through a thicker board, right? But let's say you have extremely tight tolerances on how close those traces might be hitting to a micro BGA or something. Whenever space comes into play, what we can do is do staggered vias. That's when you're kind of offsetting them because you don't have the room to keep them all the way straight or nice and uniform, right? So staggered would be another option that we do.
Yeah, and I think ICP recommends the staggered for reliability as well. So it sounds like all these mechanically formed vias are made in the exact same ways. It's just the buried and blind, we're adding extra steps, right?
Correct.
So that means there's cost staggers. Your cheapest way to design something is a through hole, if you can get away with it. And that's why I love that story about that company. You know, remember the one you saved them like 30 or 50K by helping them eliminate a buried via in their design?
Yeah, they had an extremely thick board and it was very high quantity order. And they just kept going from blinds and burieds. Then we were able to switch them over to an epoxy fill. And once we talked to them on the phone, we realized like, hey, you guys don't even need that. This is just a prototype board. Cool. Let's just do solid through holes. We can guarantee our quality. And sure enough, yeah, it saved them about 50 grand.
That's amazing. That's a neat story. Well, hey, I've got great news, Elijah. It is 11:45, and guess what the next slide is?
What's that?
DFA, right? We were going to split it DFM, DFA, We're
Yep.
on to DFA. So we're done. That was everything you need to know and more, and maybe a little less. I don't know, but everything you need to know about DFM, design for manufacturability, trying to just give you that fundamental baseline of how we make boards. Are there any questions before we let Elijah go? You guys have been incredibly quiet group today.
Yeah, we usually have a pretty good load of questions.
Yeah, it's kind of makes me wonder if there's something wrong with the software. Well, if there are no questions, this webinar will be recorded. Slides will be provided along with it and uploaded to royalcircuits.com/blog within a day or two. Next week at the exact same time, we're going to move over to the assembly process. So we did DFM today, let you know how the manufacturing process works. And next time we're going to do assembly. So with that, then, if there are no questions, I would like to thank everybody. Elijah, thank you for your time, man. It's always a pleasure getting you on one of these.
No problem. Thank you for having me.
Sure. Oh, we actually do have a question finally. So this is good.
All right.
Yeah. So the question is, what about putting a single HDI layer on one side?
Yeah, that can definitely be done. Usually HDIs are using a special material. That's something where you might want to use that cap construction like we talked about.
I would say that typically we do recommend wherever you can to use a balanced stack up. It's not an issue from the manufacturing standpoint, but at assembly time, if you have unbalanced stack ups, uneven layers of copper and dielectric material, your board can warp and potato chip as it goes through the reflow ovens. Just something to keep in mind. But yeah, it can absolutely be done depending on your things. Talk to Elijah, one of our other engineers, and we can help you talk about the feasibility of it. Any other, we've just got people saying thanks. And then here's a question, and I think it's a decent one. At what size silk screen would you bump from direct imaging to screen printing?
So the smallest we can do on a printer would be about 4 mils. And the smallest we can do comfortably on the hand silk screen would be about 6 mils, I'd say. Which doesn't sound like a big difference, but it is to the machine.
And it's also an issue of quality and readability. It's easier to see the one that's hand silk screened. I would say it's a little cleaner. The other ones come out like these little dots like you get in a dot matrix printer type thing.
Yeah,
so,
to the naked eye, you can't really tell as long as the text is big enough, I guess tall enough. And then, but if you stick it under a microscope, you are going to see that dot pattern.
Yeah. All right. Well, with that, I'm going to go ahead and end it here. Thank you, everyone. We hope you have a wonderful day, and we will see you next week at this same time. And Elijah, thank you. I'm going to stop sharing and we'll end it now.
Sounds good.
Thank you.